All right, welcome to our last Chem 1211 pre-lab video here for this semester. This week we're going to be taking a look at the Charles Law Lab, which really is going to deal with kind of gas laws in general. And so as a general kind of starting point here, kind of from a background or theory standpoint, we're going to introduce the ideal gas law. I know a lot of the lectures probably have not gotten to this point yet to talk about gases. That's okay. This is, I think, one of the easier chapters, I hope, of the semester as you're kind of going through things. It's probably certainly easier than some of the things you've been doing previously with things like bonding. So the ideal gas law, probably the biggest thing here is really just an equation in terms of kind of how different measurable variables for gases are related to one another. And for this equation that we see here, this PV equals nRT, the biggest thing is just kind of knowing what all of our pieces are. So the P in our equation does stand for pressure, and probably the most important part really of this equation in terms of just being able to use it is just to be aware of the units that everything needs, right? And so pressure is always going to be in units of atmospheres for this equation. Likewise, when we talk about the V here, which is volume, it's always going to have units of liters. We don't want to use other units in this equation, and we'll see why with the constant in a moment. The lowercase n might be a variable you haven't seen as often this semester. It does stand for moles pretty much anytime you see that lowercase n. Which I think pretty self-explanatory. The units there are moles. R for this equation is going to be a new constant that you probably haven't seen before. So this is called the ideal gas constant, hence the ideal gas equation as well. And probably the, again, important thing here, if you look in most textbooks, you're probably going to find two different values of that ideal gas constant. And if we're using this PV equals nRT equation, you want to make sure you're using this version of the constant, the one that's this 0.08206. And in particular, we use this version because of the units, right? It's liter atmospheres over mole Kelvin. Once you get to 1212, you're going to see this constant show up a lot of other times, but a lot of the other times you're going to see it, it might have different units, and that's why there's actually a second version or a different numerical value for the constant. So whenever you see a capital R in any equation kind of for the rest of general chemistry, whether it's Gen Chem 1 or 2, do just be careful about what units you need, right? So in this PV equals nRT equation, it's going to have atmospheres and liters here for pressure and volume. So we want the version of this constant that has liters and atmospheres for its units. And then the last variable here, the T, the temperature. One thing, and this is a really easy mistake to make that happens pretty often, temperature here does have to be in Kelvin to be able to use this equation. And it's pretty standard if you actually look at kind of using temperature in equations. Anytime we talk about temperature, unless it's a change in temperature, the temperature always needs to be in Kelvin for those units. Now, what we're going to be focusing on for this particular experiment is actually not the whole ideal gas law, but really just how two particular variables are related, right? The nice thing about this ideal gas law is it shows how a lot of different variables are all kind of related to one another, but what we're going to be focusing on is actually just volume and temperature. So the idea of kind of Charles' law in terms of like what it really describes, it really talks about the relationship between volume and temperature. And you can probably have some kind of just intuitive feelings here about how these two things are related. They are what we call directly related because basically as one increases, so should the other if your other variables from that ideal gas equation are staying constant. And so to kind of show that equation again here briefly, if we imagine that we have our volume and our temperature as the things we're measuring, and we keep pressure and moles constant at any point in time. So really if you just have kind of like an enclosed container that's basically going to have a constant pressure within it or a constant external pressure, like if you have something like a basketball or a balloon or something like that, as temperature changes, so should the volume, right? And we actually are probably intuitively, like I said, kind of already seen examples of this at different points in our lives. If you imagine a basketball or a balloon, as temperatures get colder, those things typically kind of almost like decompress, they shrivel or they shrink. We see their volumes get smaller, right? And if we think about this equation up here, if we think about why does that happen, well, if N and P are constant, R is already a constant, as temperature goes down, for the two sides to be equal, volume also has to go down by the same ratio, right? And then that's why what we're going to see for our lab kind of calculation-wise, we're going to be looking at a volume over temperature ratio. And we're going to be calling that kind of our Charles law constant. We'll represent it with a capital K here at the end of the lab when we see the calculations. And really, these are all constants over here on the right side of our equation. That means whatever our temperature is, our volume should be changing by a similar amount so that this ratio is constant at any temperature that we measure that ratio for, as long as those pressures and the number of moles are not changing. Now, in terms of how we're going to go about trying to basically show that that kind of volume over temperature ratio is constant at different temperatures, what we're going to be doing is actually measuring volume of air at a hot temperature, and then obviously measuring the temperature of it at that hotter temperature, and then doing the same thing just at a lower temperature, a colder temperature. So we're basically going to have two volume measurements and two temperature measurements, and we're going to try to compare that volume to temperature ratio at a hot temperature to that at a cold temperature, and hopefully be able to show that those ratios are fairly similar to one another or very close to one another. That's kind of the end goal really of the whole experiment. So it's not, I think, too complicated from kind of a theory standpoint of kind of what we're really trying to do and show in this experiment. But our experimental setup is a little bit involved, and so I do want to kind of give a kind of a quick, or say a few quick words, I guess, about that. And so this is kind of a generic image of kind of the general setup for getting our hot temperature measurement. And it's actually not even going to be the hot temperature, or I'm sorry, the hot volume measurement that we're getting from this. Basically, the way we're going to be doing this experiment, we are going to take our Erlenmeyer, just an Erlenmeyer flask. It's a 125 milliliter flask, and some things here at the beginning. What we're going to be doing is we're going to be heating this flask up in a hot water bath, and the goal is basically to evaporate all the water out from the inside of the flask. That's really what we're trying to do. And so to do that, we're going to take a water bath. We're going to make a water bath out of just a beaker. We can use a thermometer to measure the temperature of the water bath. We're going to submerge our flask into that hot water bath that we're going to heat with the Bunsen burner. And we're going to use a clamp to kind of hold that flask in place. And that clamp will be attached to a ring stand over here that would be kind of off the screen from what we see right now. But the important part is, as you're heating this, try to make sure your thermocouple that you're using, which you'll be just using LabQuest again to do this, try to make sure it's not touching the bottom of this beaker. Because if that thermocouple touches the bottom of this beaker, what happens with the flame basically blasting onto the bottom of the beaker to heat our water bath is that it could damage the thermocouple. So keep the thermocouple just a little bit suspended in the water. You don't even, if you want to, you don't even have to put the thermocouple in there until you're getting ready basically to start making measurements. So keep the thermocouple kind of just a safe height just off the bottom of your beaker. Probably do the same thing with the bottom of the actual flask you're submerging as well, just barely off the bottom. And then the other piece to really make sure of is there's going to be rubber tubing here, kind of, and actually most of our flasks, you're actually going to see the rubber tubing kind of come out the side. Make sure that that rubber tubing is open as you're heating things. Otherwise, you're going to see kind of a quick example of the ideal gas law, because if our tubing here is closed, what's going to happen is our volume is now fixed, and as temperature goes up from the ideal gas equation we had before, pressure will go up. And if the pressure inside the flask gets high enough, it'll just kind of pop the top right off your flask. And so you get kind of a quick kind of like pop, kind of to awaken yourselves if you've closed off that tube when you're not supposed to. So while heating, make sure that tube stays open. And then what you're going to do is when you're done heating and this flask has been heated at that boiling water bath temperature for like 4 or 5 minutes, then take it off of the heat and immediately clamp shut that hose. Clamp the hose shut, and then what you're going to do is you're actually going to take that flask and we're going to put it in an ice bath. And what we're going to do is when you put it in the ice bath initially, try to make sure the hose is actually still closed. And again, we're going to kind of use the ideal gas law here by keeping the tube closed when you first submerge it, cooling down the temperature. Since the volume is fixed now, the pressure will drop. And what happens is then after a few minutes of the flask being in the ice bath, we can open the tube. And when we open that little rubber tube or rubber hose, now because there's less pressure in the flask, it's going to pull some water into the flask. But it shouldn't fill the flask entirely. In fact, it should only fill up with a little bit of water. I think most times when I've seen this experiment in the past, the water is usually somewhere between about 30 and 60 milliliters is what gets pulled in. If you get less than 30 or a lot more than 60, I'd probably consider redoing the trial because your data is going to be really, really strange most likely. But that's kind of what we usually expect to see, about 30 to 60 milliliters of water getting pulled into the flask. And what that water getting pulled in does is it helps kind of equilibrate the pressures everywhere for that temperature change that we've kind of exposed our flask to. Now, once we've done this, we can measure the water that was actually pulled in the flask. We're not going to do that by reading the Erlenmeyer. We are going to use a graduated cylinder to then measure the actual volume of the water that got pulled in inside the flask itself. And then what we're also going to do after we've measured the water that got pulled in, if I back up for a second, to measure our volume of our hot flask, it's not going to be this 125. What we're going to do is after we've done the cold temperature measurement, we're actually going to go ahead and fill the entire flask with water, put the rubber stopper on it to push any little bit of water out from the top. And then what you're going to do is actually just measure how much water that took using graduated cylinders. and you should probably are going to find it's closer to maybe 140 milliliters instead of 125. That's going to be your hot water volume. So hot water volume should be bigger than 125 milliliters for all the flasks that we have. And so do not just default assume it's 125. Guarantee you will end up making some mistakes kind of calculation wise because of that and get some data that probably looks a little strange because of it as well. All right, now for the last part of this, the calculations. What we're basically going to do for our calculations is for the hot air measurements, you're going to find what is the volume of the entire flask. Right, we described that by filling your flask with water, measuring with the graduated cylinder. That's your volume of the hot air to use for the hot temperature measurements. And then you can have the temperature from your water bath. That's going to be the temperature for that hot air measurement. Now we have a volume and a temperature to basically get a volume over temperature ratio. We're going to do the same thing for the cold air. It's a little bit more particular calculation-wise, because now to get the cold air volume, you're going to take the volume of the flask minus the volume of the water that was basically taken into the flask. And what we're going to do from there, again, make sure your temperature is in Kelvin. We can now calculate these kind of what we're going to call our Charles Law constant ratios, this volume over temperature ratio for our hot measurements and for our cold measurements. And hopefully these values are pretty close together, or they should at least be reasonably close together. And what we're going to be calculating is really then a percent air. And I think the lab manual probably incorrectly calls this a percent difference, but the way it describes for you to calculate it is really like calculating a percent air. And so to do that, we're going to take the difference of our hot air and our cold, hot air and our cold air constant, or these volume over temperature ratios. We'll take their difference, and then we're going to treat the hot air as the more accurate measurement and divide by that, and then multiply by 100%. And this will hopefully just give us a rough estimation of how similar these two values are. And the lower that percent air, then hopefully the more accurate our measurements are in terms of verifying that Charles' law is true. Which there's been plenty of experience over time for us to know that it is true. So hopefully we can get some pretty decent percent errors if this lab's performed pretty well. And that's pretty much it for this week. There's not really a whole lot here to say kind of waste-wise because we're pretty much only using water. Safety-wise, we are using Bunsen burners, so do want to take the same precautions we've taken all semester. Other times we've used them as well. Be careful in their kind of handling. Make sure if you have long hair, try to make sure it's kind of tied back and out of the way so there won't be any kind of issues there. But otherwise, this hopefully should be kind of an interesting little last lab to kind of wrap up the semester with. I hope this has been a good semester for everyone, and we will have to see you next semester in 12-12.